Page 7 of Vector Apps Addendum. So we're starting with section 15H here. We're going to talk about how to solve systems of simultaneous equations using matrices, which you might have experience with, but we're going to review that, and then we're going to show how that is useful for vector and vector equations of planes. So first, look at this system, which you solved before using just algebra. And we call this a 2-by-2 system because it has two equations and two variables. Two equations, two unknowns. If we use the elimination algebraic method, then we could solve for x and y for these solutions. And those operations that we could do would be to multiply some of the equations by a factor and adding one of the equations to another or subtracting. Okay, and just to show you an example of how you might do that to do elimination is, like, the purpose of doing the elimination method of algebra is to get rid of either the x or the y, so you end up with an equation which only has x and y in it, and then it becomes a very trivial process to solve for x or y. And once you get x or y, then when you go back to one of these equations, you can easily get the other one. Okay? So like, for example, when I look at this one, I see, hey, if I multiply the bottom equation by -2, and then I add it to the first one, do you see how then I can get rid of the 2x by subtracting 2x from it? So it would end up being like 2x plus y equals -1, and the bottom equation is going to be -2x plus 6y equals -34, right? And then so if I add these, it becomes 0. If I add these, it becomes 7y. And if I add these, it becomes -35. So I end up with 7y equals -35, and y is -5, right? So you can see how the elimination strategy works, right? Now, when we use matrices, we do a similar thing, but it's just kind of a shorthand notation because we don't need to write the plus sign. We don't need to write the x's and y, the variables. And I'll show you how that works. But basically, if we were going to rewrite this system as augmented matrix, we would just write the coefficients and not the variables. So I would put 2, 1, 1, -3. You notice I did not put the x's here. I did not put the y's here, but you can see that those are the coefficients for the x's and the y's. Then I put a vertical line here to represent the equal sign, and then I put the right-hand constants on the right side. Okay, so this is my augmented matrix. Augmented meaning that I have added this column to make it into a slightly larger matrix to represent a system of simultaneous equations. And you could do this for a 2-by-2 or a 3-by-3 or larger. Okay, so, and what are the different operations you could do? I could switch these two rows. I could multiply one of the rows by a factor. I could divide one of the rows by a factor, which is pretty much the same thing as multiplying. I could add one of the rows or subtract one of the rows to another row. So let me show you how that's done by doing it on this system right here. So this would be 1, -2, 8, and 4, 1, 5, right? So let me show you what we're going to try to do. First thing we're going to try to do is we're going to try to get it in the form where we have 1s on the diagonal, 0s underneath, and then we don't care up here, okay? And if we do that, then we've kind of solved the equation, because if you look, this is equal to 1y equals something, right? And then we basically solved for y. If we can get it so that this is 0 and this is 1, and this is any number here. Actually, it doesn't even need to be 1, right? Okay, so let's do the first step. The first step would be, okay, I want to get rid of this 4 and make that 0. Okay, the way I could do that is I could multiply the first row by -4. So let's do that first. So I'm going to have -4, +8, and -32 for my first row. And my second row stays the same, 4, 1, 5. Okay? Now I'm going to add the first row to the second row, and then I'll just keep the first row the same. And then I'm going to add, so it'll be 9 and negative 27. Yeah, negative 27. Okay. And then I can easily see that now that I've put 0 there, I can have reduced this to a very simple equation, which is 9y equals negative 27. If 9y equals negative 27, guess what y is equal to? Divide both sides by 9. Y is equal to negative 3. Once I know that y equals negative 3, I can use either one of these equations to easily figure out what x is, right? So now I could say, okay, x minus 2 times negative 3 equals 8. X plus 6 equals 8. X equals 2. Okay? So you actually only need to, like, once you get, the last variable, like you do here, you can go back to algebra and solve for the other variable. Okay? You don't have to keep doing row reduction. All right. Let's go to the next section. By inspection, classify the following pairs of equations as either intersecting, parallel, or coincident lines. Okay. So when you look at these, let's write them as a augmented matrix, so you can kind of see what it looks like and how you can identify them as a certain kind of system. Okay, 0, 2. This is a kind of a tricky one, right? 0, 1, 2. Almost made a mistake there. 5, negative 11, 2. 6, 1, 8. Okay? What should you see in these matrices if two lines are parallel to each other? Well, what you normally would see is that the corresponding numbers are like proportional. So like if you saw something like this, where you have 1, 2 here, and you have negative 2, negative 4, which is can be found by multiplying the original vector 1, or the original set of numbers 1, 2, by the factor k equals negative 2. Then you found lines that are parallel and possibly coincident. Okay. Now, like if you had right-hand sides also that perfectly matched according to the scale factor, like that, that would be a coincident line. Okay, basically, like, if you have if you have x plus 2y equals 3, and you multiplied that by negative 2, and you got negative 2x minus 4y equals negative 6, this is actually just the same line. Okay, so it would be a coincident line. Okay, so here, do we have any that are proportional like this? Looking at these three, and no, none of them are proportional. Okay, so none of these are parallel. And if none of them are parallel, they're definitely not coincident. Okay, so all these are simply intersecting. Okay, all three of these are intersecting, because there's no other choice. For a two-dimensional system, there's either intersecting, parallel, or coincident. And if they're not parallel or coincident, they have to be intersecting. Okay? Let's go to number 3. Consider this equation pair. Explain why there are infinitely many solutions, giving geometric evidence. Okay, so I think that one of the geometric evidence would be kind of like graphing it. Okay, so if you were to graph these two lines, I'm a fan of slope-intercept form. So if I was going to change the top one to slope-intercept form, I would say 2y equals negative x plus 3, and then I would divide both sides by 2. I would get y equals negative x divided by 2 plus 3 divided by 2, right? And then for the bottom one, I would have 4y equals negative 2x plus 6. And if I divided both sides by 4, I would have y equals negative x over 2 plus 3/2. Oh, wait a second. Did you see? I just got the two slope-intercept forms are identical, which means they are coincident. Okay? So, yeah, the reason why there's infinitely many solutions between these two is these lines lie on top of each other, so all their xy pairs match, okay? So they are coincident, and that is why there's infinite solutions, okay? All right. B, explain why the second equation can be ignored when finding all solutions. Okay, because the second equation is the first equation times 2, right? It's just multiplied by a scale factor, so it doesn't really give you any more information than the first equation. Okay, C, give all solutions of the form x equals t, y equals something, blah, blah, blah. Y equals s, x equals something, blah, blah, blah. Okay. So in this case, if x equals t, then we could figure out the y value, because y equals negative x over t divided by 2 plus 3 halves, right? So let me just put x equals t in here, then I would get negative t over 2 plus 3 halves. So I've just found a parametric equation for y, right? Okay. And now what if, instead of having x equals t, I defined y equal to s? What would x be then? Okay, so I'm going to plug s into my slope-intercept form equation. And then I'm going to solve for x. So I would multiply 2 times both sides. I would get negative x plus 3. I'd put x over here, negative 2s plus 3 over here. So my equation for x would be negative 2s plus 3.